Salve a tutti, sono contento di darvi il benvenuto al secondo appuntamento di questa terza edizione dei webinar del PIPE, il gruppo Giovani e Non Strutturati della Società Paleontologica Italiana. Per questo secondo appuntamento entriamo nel mondo della paleontologia dei macroinvertebrati, in particolare dei brachiopodi, con un ospite che viene questa volta dall'estero, Hana Jurikova, che viene dalla St. Andrews University, dove sta facendo un postdoc di alcuni anni. Hana Jurikova ha studiato tra l'Inghilterra e poi in Spagna, per poi proseguire con un dottorato che è stato fatto in Germania a Kiel, nell'ambito del progetto Baseline Earth, che è stato un progetto che si è concentrato, grazie ai finanziamenti Horizon 2020, sullo studio della mineralizzazione e della geochimica della conchiglia dei brachiopodi, con quindi degli studi geochimici che hanno permesso di studiare, tra le altre cose, anche i vari eventi nella storia della vita sulla Terra e vari eventi della storia appunto del nostro pianeta. Quindi siamo molto contenti di averla come ospite. Peraltro Hana è una ricercatrice d'eccezione, tant'è che quest'anno è stata premiata con 2 Early Career Scientist Award, in particolare uno dell'EGU, della European Geological Union, e un altro invece della Geological Society con l'Aiel Fund che ha da poco vinto. Quindi, appunto, vi auguro un buon ascolto e cedo la parola ad Hana. Il webinar sarà ovviamente in lingua inglese e a seguire ci sarà uno spazio per delle domande e infine una chiamata aperta in cui si potrà discutere tra tutti noi sugli argomenti che Hana ha portato. So, Hana, you are free to go.
Okay, thank you very much, Alessandro. Thank you for the invitation to speak here today. I hope this will work. Let me know if you have any problems with the screen. Okay, so I'll talk to you about brachiopods, and not so much about their paleontology really, but I hope this will be still of interest to you. I'll tell you how we can actually use them to learn something about the ocean chemistry in deep time, and specifically the ocean pH. Right, so why are we interested in ocean pH? Well, it's really a key parameter of a solution. Obviously, for marine chemistry, it has huge, the changes in ocean pH have a huge impact on marine life, but also in kind of any other solutions. We measure pH using the pH scale, which was actually invented by this person here, Søren Petter Lauritz Sørensen, who was brewing beer and realized that obviously beer is going to have a very different taste and quality depending on pH. So he actually invented the scale to be able to come up with a very good quality beer. But apart from being kind of really a key solution for in any solution, key parameter of a solution, ocean pH and atmospheric CO2 are linked. So the knowledge of ocean pH, and especially of ocean pH in deep time, that's what I'm interested in the geological record, can tell us something about the atmospheric CO2. So what you're seeing here is a plot of the evolution of CO2, so measurements from CO2 from the time series in North Pacific in Mauna Loa. And you can see that if we measure ocean pH, the ocean pH kind of directly responds to changes in CO2, and it's because CO2 dissolves into the water and makes it more acidic. So if we could reconstruct how ocean pH changed in the past, we could not only learn a lot about the marine environment and its implications for marine life, but we could actually reconstruct the atmospheric CO2 levels, which are just a key parameter for the climate. Okay, so if we think about Earth's kind of geological record, we've got loads of fascinating events and environmental and climatic changes. And the key question that I'm asking here, and we're interested to find out, is what was the role of ocean acidification in them? Did it play a role? Could it be that loads of the mass extinctions where we see disappearance of marine calcifying organisms are perhaps linked or perhaps were influenced by changes in ocean pH. And most importantly, if we have this parameter, we can again not only learn about those extinctions and what was causing them, but also actually reconstruct the CO2 and think about the climatic implications. Okay, so how do we reconstruct ocean pH in deep time? And it's definitely it's not an easy task. And the key thing that we need for it is an archive. It's an organism that's preserved and that we can read information on ocean pH from. And what I use is our brachiopods, and I've been, I'm by training really an isotope geochemist, but I'm absolutely fascinated by brachiopods, and especially how abundant and diverse and often well preserved they are in geological records. So what you can see here are some really fantastic outcrops that we have around Scotland, where this is a mine with a ceiling full of brachiopods, and you can see even carboniferous brachiopods can have this really exquisite preservation, and loads of intervals in Earth's history that are interesting are actually found as well, kind of filled with brachiopods mostly. And you might wonder why that is, and actually the key thing here is that their shells are made out of low magnesium calcite, and low magnesium calcite is the most stable calcium carbonate polymorph when it comes to diagenesis. So you can find brachiopods that are 250 million years old, like, for example, it is shown in this image here, which microstructure looks absolutely kind of similar and identical to the microstructure of a recent brachiopod. So here you can see an example from Magellania venosa. This is a recent brachiopod that we've worked a lot on. And then here you can see the same kind of fibers in a Permian brachiopod. And you can often see kind of the fibers and the structure already under the microscope. So when you're collecting samples from these, this is what I do most of the time. I try to pick really well preserved kind of pure nice shell flakes that we can then look at through a geochemical lens and think about the marine environment. So you can already see them often, very well preserved just under the microscope. But obviously we do apply a thorough petrographic and chemical and screening to check their preservation. Okay, so we're talking about brachiopods, but what are they actually? And this is really interesting because we know a lot, and I'm sure and geologists know a lot about brachiopods, but there's actually not so much or research done on modern brachiopods, and that's really critical to us. We need to understand how they grow, how they make their shells, so that we can actually make interpretations that are reliable and robust from the fossil brachiopods. So brachiopods are nothing like mollusks. Their definition is something somewhat ambiguous. They are a group of marine bivalve lophophorates with an ambiguous definition, but distinct mineralized and non-mineralized morphological features. So as shown here, so they can look like bivalves, but they're nothing like bivalves really. And actually, they're more closely related to phoronid worms shown here, or even bryozoans. So a very different organism to what you would expect based on their kind of bivalve appearance. And the great thing for us trying to reconstruct how ocean chemistry and climate change through time is that they are, as I mentioned before, they're really abundant and really diverse in different environments and through most of the times of the Paleozoic especially, but also Mesozoic and Cenozoic. And we do have them around today, and we can study and learn from them. So a lot of the work that kind of I've been doing, and actually kind of where most of my research really started, was looking at living brachiopods. So I'm going to mute this. And this is, as I said previously, this is really critical. So what you're seeing here, it's a video from an underwater expedition to the Canary Islands, where we went as part of the Baseline F project to look at modern brachiopods. And we wanted to understand how they grow, how they live, but also collect some so that we can measure, collect the water, monitor the water conditions, and see how the water pH is reflected in their shells. And in fact, we also took them into alive to kill and culture them, which you'll see in a bit. So what you can see here is this a brachiopod called Paiodina atlantica that inhabits this crevices and caves in La Palma. And although often, you know, brachiopods are no longer really seen on the coast, or people are not so aware of them, if you really look at the right spot, you can find these kind of wonderful populations that are just, you know, and spots that are just really filled with brachiopods. So you can see us here taking some of these samples, and then we've been, you know, culturing them to learn and really kind of calibrate well the tools we have to reconstruct changes in ocean pH and also other environmental parameters in the past. And here you have one more and last video where you can see this time a different brachiopod species. This is Magellania venosa, again, a brachiopod that we've been looking at. This is actually the largest living brachiopod that can be found on Earth today. And these, and together with the Paiodina atlantica, we've been culturing them and figuring out how well their shells can reflect ocean changes in ocean pH. Okay, so yeah, we've conducted these culturing experiments to calibrate the proxies, geochemical proxies, but also other, you know, more structural and lots of other, you know, exciting work was done on this. Not only looking at changes in ocean pH, we've cultured actually brachiopods under extremely acidic conditions. So if you think about it, that kind of modern ocean has a pH of around 8.1. We've successfully cultured brachiopods at pHs values of 7.3, which is really, really acidic. And it just shows their kind of remarkable ability to survive in very harsh conditions, and which actually perhaps also explains kind of why they are, you know, very diverse and abundant throughout most of the geological record, and even on, you know, still found on Earth today. Okay, so what we've been mostly looking at, so we've been looking at all sorts of proxies, but obviously we're interested in reconstructing ocean pH, and I don't want to get into kind of all of the technical details how we do that. We use the but I do want to say that kind of the main proxy that I use for this, and we've been calibrating and interested in, and I've been interested in, is our boron isotopes. It is perhaps the best proxy that we currently have for reconstructing ocean pH and CO2. In fact, kind of loads of our knowledge on how ocean pH and CO2 change throughout the Cenozoic comes from forams, and one kind of key outcome boron isotope measurements in forams, and one of the key outcomes of this work is that actually we can, you know, brachiopods reflect reasonably well pH as forams do, and we can kind of construct the calibrations that we know from forams, and with that really push some of these records and work that traditionally is, you know, is known mostly from the Cenozoic into deeper time. But we also have lots of kind of other tools, like looking at the microstructure that we can use to infer changes in ocean pH. And this is, I'm showing here a figure from a wonderful work by Fasheng Ye, who was also part of the Baseline F project, who kind of was really able to show that the changes in pH really affects the microstructure. And this is also something that was previously used by Claudio Garbelli in this fantastic paper where he kind of hinted at the changes in ocean pH during the Permian Triassic mass extinction by doing this really meticulous work of measuring the fibers and the structure, and then looking at the changes in pH. So there are lots of proxies that we can use, and we've been learning about thanks to this culturing. But kind of one point I do really want to make, that being able to actually apply boron isotopes is really fantastic, because it's a quantitative proxy, and we can, with this tool, we can now actually reconstruct the absolute change in ocean pH values, and also get to the CO2 values, and then reconstruct the CO2 that was behind the pH change because of the tight coupling between ocean pH and CO2. Okay, so oops, sorry. So right now, I want to kind of give you an example of what we can do, having these tools and understanding, you know, how brachiopods grow and how they incorporate boron, and having these tools, what we can actually learn from geological past. So obviously, where to start? We now have our archive, we have the tools, we have the whole geological record. Well, obviously, you know, the Permian-Triassic mass extinction is perhaps, right, is one of the most fascinating events in Earth's history. So it's an obvious one to start. There's been loads of work that suggested that ocean pH could have played a role, but it's been difficult to reconstruct. So I've been really lucky to kind of to have wonderful collaborators that were willing to provide samples that we could measure and look at and see if we can apply boron isotopes to learn something about ocean pH. One kind of thing to kind of stress is that, I'm sure you all know, Permian-Triassic mass extinction is the largest mass extinction in Earth's history. But what's been really interesting about it is that we also have, it's kind of in the sediments, it's captured by a huge negative carbon isotope excursion, and that points to an input of light carbon to the ocean atmosphere system. And our kind of best geochronology of this event actually suggests that its event's been really, really short. And how can you produce such a huge change in the carbon cycle within such a short time has been quite difficult to explain without the knowledge of the CO2 behind. If that was caused by CO2 behind, can actually CO2 explain it? That is another question. So making a record of or getting information on ocean pH is not only relevant for understanding why, you know, loads of marine calcifying organisms disappeared, but also can allow us to actually, you know, find out what happened in the climate system. Okay, so kind of, again, I don't want to really get into all of the details, but what we did is we measured a whole bunch of brachiopods that, you know, boron isotope composition of brachiopods before the interval, and then like going right into the extinction in the very latest Permian. Potentially we have actually some samples there just across the boundary, and what we found is this huge change. It's around 1.5 per mil in boron isotopes. That's really big in the boron isotope values, which point to changes in ocean pH. And having this information, we can actually you know, reconstruct the changes, and we found that the ocean pH changed by around 0.5 pH units. So you need a lot of CO2 in a very short time to be released to produce this change in marine system. So once we have these parameters, we can actually, you know, reconstruct the CO2. So we were able to constrain the CO2 in the late Permian and the early Triassic. So we find a spike from around 800 to 4,000 ppm. For comparison, I mean, kind of context, CO2 today is you know, just about 400 ppm. So this is a huge increase in atmospheric CO2. And when we have this information, we can actually also think about what was the forcing necessary to explain, to cause this change, and what would have been its delta carbon isotope composition. So point I want to make that having the information on ocean pH not only allows us to reconstruct the CO2, but also think about where that CO2 could have come from. And thanks to this information, we're able to run models, and those models are allowing us to diagnose the origin of the CO2. And kind of the key outcome of this study is that to explain the patterns, the changes in carbon isotopes, in boron isotopes, the records that we see throughout the Permian-Triassic boundary, is that we need huge CO2 release caused by metamorphic degassing of organic-rich sediments. We've been able to calculate that actually more than 100,000 billions of tons of carbon was released during this interval, which to put in context, is more than 40 times the size of modern carbon reserves, including the carbon already burned since the Industrial Revolution. So that's a lot of carbon released. And it's not actually coming from the mantle from, during the Permian-Triassic times. We have this large igneous province called Siberian Traps that these flood basalts dig us in CO2. But it's actually the magmatic intrusion into coal sediments, so into your ancient fossil fuel reserves, that was able to produce this huge amount of CO2 that was necessary to kick off the extinction, the climatic and environmental changes that then later led to the extinction. And the second point is that I want to make is that we can not only reconstruct what was the pH in CO2, but we can, these two parameters are so critical that we can actually think about the whole biogeochemical cycling at time and all sorts of kind of key conditions and processes on Earth. And I do not really want to get into details, but just kind of want to almost wrap that up, is that thanks to this, we've been then able to basically show that it was the CO2 release that caused kind of a greenhouse effect in the first instance. So we have a huge warming and ocean acidification that's creating greenhouse effect on the environment, and that explains a lot of the disappearance patterns of fossils, the fossil patterns that we're seeing in the record. So we see carbonate producers disappear quite early on. So you would have huge ocean acidification and warming wiping out ancient coral reefs in the very kind of latest Permian. And then later on, there's profound changes to the environment and changes to weathering as a result of the increase in CO2, changes to biological pump, consequent changes to biological pump and marine redox chemistry, then are actually able to cause anoxia and euxinia that explains the kind of the later disappearance of organisms that we know from this Permian-Triassic mass extinction. So I hope that I've kind of convinced you how important that we have a tool. We now have a fantastic archive. Brachiopods make a fantastic archive that allows us to read how ocean pH and change through time, and in fact reconstruct the CO2. I hope I've convinced you that we now actually have a really good understanding of what happened through through the Permian-Triassic mass extinction, thanks to this information. And we've been trying to apply this to other events. There's a lot more work in progress that's coming, and I kind of didn't want to really show today because I'm not sure how much of that I should be really showing. But there's, I'm really happy that with this we've been able to learn, but also hopefully inspired a lot of work that's now looking at different times of the Earth history. Tamás Müller also published a really nice born isotope record from the torsion ocean anoxic events. So we've learned a lot from that times, and we're kind of looking, as said, into other times. This is really only possible thanks to wonderful collections and collaborators, and I just really want to kind of stress here, as shown in the image, this is a collection, I believe, from the University of Milan, that Marco Viaretti and previously also Claudio has been working with, and obviously Lucia Angelina has been kind of taking care of, and it's been really key in kind of supporting this work and kindly contributing samples and knowledge so that we can look and reconstruct these wonderful events from Earth history and learn more about the environmental and climatic changes. I think I'll leave it there. I just really want to thank you for inviting me here to speak today. I want to thank again all agencies, colleagues, and collaborators, students that have been supporting this work and providing samples. And I'm happy to take any questions and discuss this, whether now or later, discuss this further. Thank you. Also.
Okay, so thank you very much.
Yeah, thank you. Also, I'm not really sure what the time is because I couldn't see anything except for my screen, so I couldn't see. And I hope that kind of all worked out, because it's been a bit difficult to see everything. So yeah.
Perfect and very interesting. So I don't know if there are. Yeah, we have some questions from the chat. So I'm going to read it for you. So, is it possible for sediments rich in organic matter to release carbon compounds right now? Present-day acid rains and global warming may play a role and lead to notable gaseous releases from old sediments.
Sorry, could you repeat that? I'm not sure if I quite understood the question.
Okay, so the question basically is about actual extant release of carbon. So actual release of carbon from organic rich sediments right now.
Yes. I think the question is if that can contribute, right?
Yeah.
Yeah,
so I think that something similar can happen nowadays.
Yeah, I mean, it's nowadays, obviously, or you mean in the past?
No, nowadays. The question is about extant nowadays.
Okay, well, I mean, nowadays, obviously, lots of, the carbon released to the atmosphere primarily comes from the burning of fossil fuel reserves. So that's your kind of, right, your ancient organic carbon that's being burned, but by humans. But I guess you could. I mean, I'm not quite sure if I'm understanding the question correctly, but I guess you could have you some carbon release from the sediments. I mean, in general, also, or at least I can speak for the past, the organic side of the carbon cycle is not as easy to constrain as the inorganic, at least in the geological record. So there are some questions that we kind of still have about that. So most of my work really focuses at trying to constrain the inorganic carbon cycle.
I see, yeah. And so the same person also asks if brachiopod fossils in organic rich sediments show peculiar characteristics which are different from non-organic rich sediments. Also, if I think that you didn't just select organic rich sediments to sample your brachiopods, isn't it?
No, so I've mostly worked on samples that have been previously kind of characterized and screened and really selected. But I have not really looked in great detail. I can imagine that obviously the environment in which your sample's buried is going to really matter, and it can affect the preservation. I mean, not all brachiopods are well preserved, right? But I guess the point I really want to make is that if you can select them correctly, and if you work on the best preserved brachiopods, you can really come up with these records that are start to look almost similar to something we know from relatively younger times, and we previously thought that might not be possible in Earth's deep time. So I could imagine that would have an influence, but I've normally kind of specifically worked on samples that are very well preserved and come from conditions that represent the kind of the general ocean setting. So yeah,
I see. Okay, so also from the chat there is Marco Viaretti, which we all know, which says, Hana, great talk, and was great to see some living brachiopods.
Yes. Thank you very much, Marco. Yeah, I specifically, I hope you kind of, I know that the audience is mostly paleontological, but that's why I specifically wanted to perhaps provide a slightly kind of a different focus to this, because I know we see a lot, brachiopods in the geological record, but there's lots of interesting stuff to be learned from modern brachiopods. And I personally was really fascinated by what we can do and how much we can really learn by studying them, and how much room there is still to kind of learn more. So yeah, I'm glad to hear when a paleontologist says that they enjoyed the living brachiopods as well. Okay,
so we have our two questions actually. So Another question is, how long did the acidification of the ocean last after the Permian-Triassic event? And was the acidification the same in all the oceans at the time?
Oh, that is a great question. To be honest, I'd like to know as well. So obviously, you know, we can only reconstruct so much where we have brachiopods and samples, and our work only goes kind of to the perhaps the very earliest of Triassic, but we do not. I've been desperately trying to find actually early Triassic brachiopods, and it's been a very hard task because there's just pretty much none. So I do not know, and I think that is a very interesting question for kind of understanding the whole Permian Triassic puzzle a bit more. Perhaps we know now more about the extinction, but what were actually the kind of the impacts and the further on consequences and what was happening in the early Triassic. So it'll be fantastic to know what the ocean pH was. We don't know, simply because we've not been able to. Nobody's really been able to reconstruct that. There's no brachiopods. If we had some, we could. And so in our record, we just go from the very late Permian to kind of the early Triassic. In our model, always kind of, if you model this, for example, your model normally tends to predict that because of the silicate weathering feedback that consumes CO2, atmospheric CO2 will get consumed, and as a result, your ocean pH has to go up. But how effective the silicate feedback was in the early Triassic and to what extent the ocean pH rebounded or not is something we've not been able to actually reconstruct.
I see. And do you think that you had, I mean, of course it's difficult to know, but what about differences in pH between different localities and oceans? Do you think it might be possible to map that, or you can just have a global signal?
Sure. I mean, right now, in these times that we like to think about the signals being global, and we do have a good justification for our signals to be global, which is because we took samples we kind of made a record from the Dolomiti in northern Italy, from the brachiopods from there, but we also had few samples from the other side of the Tethys Ocean back then, from the Shaanxi section in South China, and actually the results we get are really the same. So it's very convincing to have samples and brachiopods that show very similar values from two different sites. So I think that is a really good argument for a more global-like signal, and that these data are not biased. And also, if you look at other isotopes, for example, even carbon, oxygen, but also kind of other your general composition of the brachiopod, if you can see whether it reflects the marine environment, the general marine environment, or maybe lived in some lagoon and was biased. So we're quite confident that all our samples reflect more of kind of general ocean pH. But that said, it would be really, and I think this is a way to go forward, it would be fantastic to have records from different places, and not only to see if there was an acidification. I think there would have been acidification everywhere, but perhaps some environments are not acidificating as quickly, or they have something else is going on. So that would be really good to see. It's just so challenging, with these records to do that, because it's hard enough to find brachiopods for the Permian Triassic mass extinction from one place. So to get brachiopods from several locations, that is a big challenge. But if you have any, that'll be great to do. Yeah.
Great. So there is another question by Marco Viaretti, which is interested in living brachiopods today, apparently. And so he asked how difficult it was to culture them. And also he says that in your video, and I noted that as well, you have some shells closing. So Marco asked if that's due to some people passing by, and so causing maybe some shade so that the brachiopods should close.
Yeah, that's it's interesting. Yeah, that was me kind of trying to tap on the screen, because I keep getting these comments from everyone. The brachiopods are terribly boring, and I mean, I've heard that you had a dinosaur talk last week, so I don't know if brachiopods can be that, but I like to think so. But anyway, we've been trying to get them to do something so that they look a bit more interesting on the video. So if you kind of really react and tap the screen, they'll close. So that was that. And well, in terms of the culturing, well, we thought it was really difficult. People kind of used to think it was almost impossible to culture them, that they wouldn't survive, and let alone if you kind of, not only you want to culture them and kind of reproduce the environment, you also want to then stress them so that you can measure their response, whether in terms of geochemistry or shell structure or what sort of proxy parameter you're using to see how well they reflect, to learn about them, but also see how well they reflect changes in ocean chemistry. So yeah, we thought it was very difficult, but we did manage. They actually, you know, we were surprised. They did very well. I don't know if they, you know, the labs where we did that were really fantastic. So, and people, you know, we've been lucky to kind of have the expertise and experience of people that cultured loads of difficult organisms from very kind of interesting environments. So I think we've just been lucky, because culturing is never easy, and you know, they can all die, and then that's it.
I see. Okay, so I think that in 10 minutes or so, this call will be closed and our live will be closed, but we will move to another call, which will not be broadcasted live, but will be open to everyone. So we will send the code, Google Meet code, to enter in this call in the chat, in the YouTube chat. And I will send to you by email, Hana. And so there is another question, actually, from Professor Angelini, which is, did you see a different reaction in culturing under low pH in Paiaudina versus Magellania, which has a very different microstructure?
Oh yeah, it's a great question, and hi, Lucia. Well, the problem with the Paiaudina is that they're really small. They're really tiny, and when we were culturing them, we actually really struggled to get enough material to do geochemical analysis on them, at least back then, with the kind of amount of material we needed. So because they're so small and they grow so slowly, they really, like, the new grow on the shell after 2 years of culturing, and that is a very long time to kind of culture and run those experiments and have to have, you know, we had to measure the chemistry of the cultures almost on daily basis. We had to feed them regularly, you know, on weekends, holidays, they don't care, obviously. So it's been a huge kind of challenge, not only get everything set up beforehand, but then culture them for more than 2 years. So, and in those times, the Paiaudina, they grew really small amounts, kind of really almost microscopic amount, because they are just so slow growing. So we've not been able to do, at least at that time, we couldn't do any geochemical analysis on them in terms of boron isotopes or other isotopes, really. But right now we have lots of kind of new tools that allow us to do high resolution measurements, and perhaps that's something really to get back to and have a look at, because I'm quite confident that right now, with using laser ablation or SIMS, we would be able to measure just the material that was grown under the specific, let's say, very low pH conditions, and then compare it to the newly grown material from higher pH conditions, and learn something about the pH from geochemistry. Yeah, I'll be actually interested to know if because I know Lucia's well, I can ask at the time, but it'd be interesting also to know if what was the impact on the microstructure, which I don't think we really kind of, again, had the opportunity to look at, because they were just so small.
Yeah, this can be discussed in the call.
Yeah.
Now. So I don't see any other questions, and it was great to have so much questions with brachiopods, because, as you said, after dinosaurs, you never know, but in the end, brachiopods had interested a lot of people, so I'm very happy about that. E quindi passo all'italiano per i saluti finali. Ringrazio tutti voi che avete seguito, e ricordo che comunque il webinar rimarrà online da adesso in poi, dopo un paio di giorni in cui lo sistemeremo, quindi potrete fruirlo anche dopo, rivedere delle parti e eventualmente anche condividerlo con altre persone che potrebbero trovarlo di proprio interesse. Io ringrazio molto Hana, che è stata molto, molto brava. Ringrazio Riccardo Rocchi, che anche questa volta è stato alla regia e perfettamente. E quindi vi auguro una buona serata, e per chi invece volesse approfondire i discorsi che abbiamo fatto con una chiacchierata dal vivo con Hana, appunto trovate nella chat di questa live il codice per la chiamata. Buona serata a tutti.